Hi everyone, welcome to my talk. I'm Narayanan Rangaswamy from Duke University, and I'm going to talk about a classical coding problem from quantum T-gates. So let me share my screen, my slides. Okay, so let me get started. So this is joint work with my advisors Robert Caldebank and Henry Pfister, and Michael Newman, who was a postdoc at Duke. So this talk is primarily based on the ISIT paper, which is this link, and the longer version of this paper is here, and it builds on prior work that I'll explain as I proceed. Okay, so let me start with some quick motivation. Let's say you have some k qubits of information, and you want to process that information. So you want to do some quantum operation, which could be a unitary operation or a measurement. And if you did it ideally, you would end up in the state x tilde. But unfortunately, all operations in the lab are noisy. So if you did this directly on your raw information, there is no way to protect from errors, and you wouldn't know if you made a mistake. So instead, we use the concept of a quantum error correcting code, where you encode your information into a quantum error correcting code. So NKD means you have k qubits of information that you're encoding into n qubits, n larger than k, and d is the distance of the code, which means an error must act on at least d qubits for it to go undetected. So once you have encoded, you can do operations in the lab on these n physical qubits, and you end up in some final state. Now, if the errors remain correctable, then the code will help you correct those errors. And if everything goes well, you will be in the right state at the end. And finally, when you decode, you will hopefully end up in the state that you desire. So your logical information underwent a transformation indirectly by processing these physical qubits in the lab. Now, if you wanted to do this and do this right, then of course you need to make sure that the logical operations are translated to physical operations on n qubits in the right way. So for every operation, every k qubit operation, you need to find the right n qubit operation to do, and you have to do it in a fault tolerant way. Now, a fundamental question here is, if you're doing a physical operation in the lab, obviously you want it to map code states to code states. So you want the code space to be preserved. You don't want to go outside the code space. So how should you design your code such that a given physical operation preserves the code space? So that's a question you want to have in mind. Now, our key idea here is to use the fact that poly operators, which I'll introduce shortly, form an orthonormal basis for all n by n matrices. So this is a fact that has been known for a long time, but it does not seem to have been used as much in this context, as I'll explain later. Now, our steps, we have like 3 steps. So you pick some gates. I'm being vague here, but this is just to emphasize that although the talk is about T-gates, there is in principle a general recipe that you can use. So you take whatever gates you're going to do in the lab and understand their action on poly matrices, which form a basis, and then use this action to understand how these gates affect the code subspace, and then you derive conditions for when the code subspace is preserved. Once you do that, now you can just restrict to gates that are reliable in the lab, because it doesn't make much sense to take very noisy gates in the lab and try to do something useful with them. So you take gates that have high fidelity in the lab and do this process. So that's the general strategy. Now, to connect it with the literature, the closest literature is the magic state distillation literature. So this talk is not about distillation, so I'm not going to go much into details. But this was an idea introduced by Bravi and Kitaev in this paper and has been quite influential. So there are these concepts that have been developed over time in order to make good codes for distillation. So, and we make explicit connections between our work and these works. Now, one primary distinction between these works and our work is that these works use what we might call the Schrodinger perspective, where they look at CSS codes, which are a specific kind of quantum codes, and then they try to see what these gates that I mentioned, how they act on the basis states for this CSS code. So the CSS code is a subspace, and the subspace has a basis. So you take these gates and make them act on the basis states and see how they act. And based on that, you derive conditions for making sure the gates do what you want them to do. That's their approach. We use what you might call the Heisenberg perspective, which allows us to first generalize beyond CSS code. So we are able to work with arbitrary stabilizer codes, and CSS codes form a special case. And the way we do it is, instead of looking at these basis states, we look at the operators for which these states are eigenvalue 1 eigenvectors. So meaning the operators that fix the state, and we evolve the operators through the gates that we do in the lab. And that's an equivalent approach, but it's more general because analyzing basis states of non-CSS stabilizer codes is usually hard. Okay. Now with that high-level motivation, and let me set up some quick notation. So the polymatrices that I just mentioned are the so on a single qubit, it's the 2x2 identity matrix, and these three matrices, X, Z, and Y. Let's not get into the details of how these matrices look. It's not important for the talk. So on a single qubit, you basically have identity X, Z, and Y, and products of these operators. The key structure in the group is that any pair of non-identity matrices anti-commute. So XZ equals minus ZX, and similarly XY is minus YX, and ZY is minus YZ. Now, because you only have four types of polymatrices, I, X, Z, and Y, you can use this shorthand notation of two binary vectors A and B on small n qubits. So here is an example for 3 qubits. Now, when I write 1, 0, 1 on the top, so for A, and then B is 0, 1, 1. So you look at qubit by qubit. So the first qubit, only A is 1, which means the notation is that you're only applying X on the first qubit. And then second, this part is 0, so there is no X. But B is 1, so you are applying Z. And if both are 1, then you're applying Y, because Y is actually square root of minus 1 times X times Z. So that's the shorthand notation. So A you might call the X component, and B the Z component. So all polymatrices on small n qubits can be written as EABs up to multiplication by some fourth roots of unity. That's the full Heisenberg-Weil group, or the poly group. Now, like I said, the key structure in this group is that pair of polymatrices commute or anti-commute, and in this binary world, you can capture that by this symplectic inner product. So if this inner product is 0, then EAB and ECD commute, and if it's 1, then they anti-commute. Okay, that's the poly group. The Clifford group is defined as the normalizer of the poly group in the unitary group, which means by conjugation, it maps polys to polys. Now, so to be more precise, if you take any Clifford G on small n qubits, and you conjugate any polymatrix by G, so G dagger is just the Hermitian transpose, which is also the inverse because G is unitary. The result is up to some plus or minus sign. The result is a polymatrix that is described by a symplectic transform on the binary vector. So FG is a symplectic matrix, which is a binary symplectic matrix of size 2n by 2n. And this condition means that it preserves this inner product. So before and after the transformation, the structure of the group is preserved. And so what you need to remember here is that once you represent polymatrices as these binary vectors A and B, then Clifford matrices, you can just think of them as these binary symplectic matrices. While G is actually 2 to the n by 2 to the n, these symplectic matrices are just 2n by 2n and binary. So that's a big reduction in complexity. The other concept we need is that of stabilizer codes. So an R-dimensional stabilizer is described by R commuting polymatrices. So each generator can have a sign plus or minus 1, and the span of these generators should not contain minus the identity. Now the NKD stabilizer code is defined as the subspace of n equals 2 to the n, such that each state is fixed pointwise by every element in the group. Now here is an example. for a 642 code. So you have 4 logical qubits and 6 physical qubits, which means you have 6 minus 4 equals 2 generators for the stabilizer group. And we picked these generators to be X on all qubits and Z on all qubits. So the binary notation, that means X on all qubits has X component all ones and Z component all zeros. And similarly, Z on all qubits has Z component all ones and X component all zeros. And the span of the group is just the row space of this matrix. Okay, so those are the key background things we need. Now let me introduce this notion of quadratic form diagonal gates that we came up with a little while back. So here is a table of the commonly used matrices in the lab, operators in the lab. Now for universal quantum computation, there is a finite set of matrices that can arbitrarily well approximate any unitary matrix. So the set can be split into two things: the Clifford group that I just introduced, which is generated by these 3 operators, and the T gate, which is a non-Clifford gate. Now for the Clifford operators, you can write their actions on polys, and then you have the symplectic correction. But for the T gate, it is non-Clifford. So for example, it maps the poly matrix X to X plus Y, which is not a poly matrix, which is in fact Clifford. So the question is there any hope of extending the symplectic formalism to include some of these non-Clifford gates? Now we'll specialize on this form, this red form, which captures these phase gates, for example. Now, if you look at the T gate and the phase gate, the main difference is just this, the root of unity. So this is a 4th root of unity, this is an 8th root of unity. So the idea we had is that while the phase gate can be written in this form, where R is a binary symmetric matrix and VRV transpose is computed over Z4, what happens if you replace I with Z, with e to the I pi over 4? You can definitely represent T like that. And the question is whether that has a nice mathematical structure. So let me introduce QFT gates now. So there is this notion of a Clifford hierarchy. I won't get into the details. The first level is the poly group, and the second level is the Clifford group that I introduced. And these are just the diagonal Cliffords that we saw on the previous slide. So the standard diagonal Cliffords are the phase gate and the control Z gate. Now, what we did is we tried to extend it to higher levels in the hierarchy. So we defined gates that are of this form. So we just replaced I with a 2 to the Lth root of unity for the Lth level. And now the exponent has a R, which is not binary symmetric, but integer symmetric, with entries in the ring of integers mod 2 to the L. And this quadratic form is computed over this ring. So that's our generalization. And you can see that T can be represented like this with the same symmetric matrix as P, but it's interpreted over Z8 instead of Z4. And similarly, the square root of control Z is called the controlled phase. So you take square root of -1, you get I. And it also has the same symmetric matrix representation in this QFT formalism, but now you interpret it over Z8. And you can keep growing. So square root of T will still have R equals 1, but it will be over Z16 and so on. So all single qubit and 2 qubit diagonal gates can be written as QFT gates. So that's all 1 and 2 local, which is just single qubit and 2 qubit gates, and tensor products of them are QFT. Now, what is more important is that they have a nice structure. So when you make them act on poly matrices, you get an action that is very similar to that of Clifford. So if you just compare term by term, for Clifford, you have this phase. Now you have a more general phase. And you had this binary symplectic transform. Now you have an integer symplectic transform because R is an integer symmetric matrix. And we actually work out the details in the paper. So this is, again, just a symplectic transform, and this is a symplectic matrix. But the story stops there for Clifford, whereas for this QFT, you can have an extra thing, which is also QFT from a lower level. So an L-1th level QFT gate that is described by a symmetric matrix R tilde, which is a function of the parameters you started with. So there is this very nice recursion, which has a product form, which has a recursive product form of a phase times poly times a lower level QFT. So you can find more details in this paper, and this insight could be useful for other applications. Now, what we are going to do with this is we are going to come up with conditions for stabilizer codes that are preserved under the application of T-gates, which is a special case of QFT. So you might remember this diagram from the beginning of the talk. So like I said, the ideal thing we want to do is translate any logical operation to physical. And this is actually what we do for logical Cliffords in this paper. But this is hard to do beyond Cliffords, at least for now. So what we do instead is ask the reverse question. So if we apply physical T-gates in the hope of realizing, say, a logical non-Clifford gate, then how should I design my code such that the T-gates map code states to code states? That's the question we are going to answer. So let's just set up this formally. So when is transversal T a logical operator? So an equivalent question is, when does transversal T preserve the code space? So you pick an arbitrary stabilizer, and because it's a subspace, there is a projector to the subspace, and it turns out that the projector is just a superposition over all elements of the stabilizer group with the appropriate signs, plus or minus 1. Okay, now once you have this, we want to understand how this T-gate acts on the code projector. So we are going to conjugate the code projector by the T-gate. And when you conjugate by linearity, you conjugate term by term. So you want to understand how T-gates conjugate on EAV. And that's the first result we derive. So what this does is this takes the QFT formula that we saw before, which had this product form of a phase times poly times at lower level QFT. So it takes that and it computes the poly expansion, because polys form a basis. You can expand that product form as a sum of polys. This can be in general hard to do for more general QFT gates, but for the transversal T case, it turns out to be doable, and it's quite a nice calculation. Now, once you do this, now you can look at conjugating the code projector. And when you conjugate the code projector, if you do it term by term, then you can just take this formula and plug it in there. So that's what is highlighted here. And you preserve the code space only if the code projector remains invariant under the action of these T-gates. So this has to be equal to your original code projector. And we solve this equality completely in the paper. We derive conditions for the stabilizer group under which this equality holds. But I won't describe the general theorem here because it's a bit complicated to describe. But when you specialize to CSS, you get this condition that you have a pair of binary codes, C1 and C2. Where C2 is a subset of C1. So the C2 is an even code. And the second condition you need is for every code word in C2, the dual of C1 contains a self-dual code in the support of the code word. So you just look at the non-zero entries in X, and under those indices, there has to be a self-dual code inside C1 code. This should be true for every code word in C2. So that's the classical coding family we desire. So once you have this family, the quantum code has these parameters, n, k1 minus k2, and distance. Now, two corollaries from this that we prove is that the triorthogonal codes described by Bravi and Ha is the only CSS family where transversal T physically does logical transversal T. And for every NKD non-degenerate stabilizer code that supports transversal T, one can also find an NKD CSS code that does. So CSS codes are optimal among non-degenerate codes for transversal T. Now, the open problem that we have come up with is to find a constant rate family here, the constant rate CSST family, and also say linearly scaling distance. So this can be too strict. So log scaling might also be fine, but linear scaling would be amazing. So that's the open problem. And if this is solved, then you can get what's called constant overhead magic state distillation, which means asymptotically, this parameter goes to 0, which is crucial for distillation. Okay, so let me summarize. So I introduced QFT gates in this talk and described their action on poly matrices. Then we use the QFT framework to compute conditions for when a code space is preserved. And in the paper, we have extensions to smaller angle Z rotations other than T, and we have examples of Reed-Muller codes. And one open question is can we extend this beyond T gates to other QFT gates? And this is the key takeaway from this talk. So expanding unitary matrices in the poly basis seems very useful. Those are my references, and thank you very much. Thank you very much.